Welcome back. So in the last class we have discussed about the weak formulation by adopting Galerkin method. How we can develop the weak formulation by equating the integral of the partial differential equation to 0 by thereby also we can minimize the value of the residuals. So now we will go forward to discuss about the development of element matrices. Arriving at the set of finite element equations at each nodal point of a given element based on the PDE, the governing equation that we are solving in the domain. So the finite element model based on the weak form transforms the differential equation into algebraic equations for nodal values u I e, primary variable and secondary variable, that is q I e, incorporating natural and essential boundary conditions. So it allows flexible interpolation without predefining the approximation degree, supporting various levels of accuracy. So here the solution u is approximated using Lagrange interpolation function psi j x of degree n minus 1. So how we can write u here? So here u we can express as u is equal to summation of j is equal to 1 to n u j e shape function psi j, which is a function of x. So this is how we can express the primary variable u. So where u j e are the coefficients at the nodes of the element. So the weak form now can be expressed. So please recall in the last class we have discussed about the differential equation that we are choosing for generating the weak form, and then so this is the weak form of the differential equation, that is we have discussed earlier, but for your ease I am writing it again over here. So a du dx plus C u minus f is equal to 0. Okay. So this is the differential equation that we are basically trying to generate the weak form for, and this is the weak formulation when we are equating the integral of this equation to 0. So you can see we have already discussed in the last class about how we have arrived at this expression over here, and we will now proceed from here on. As we have written, so now here in this we can simplify this expression as by the series which is from I is equal to 1 to n minus 1 integration x I 1 to x I 1 plus e a dw dx du dx plus c w u minus w q dx minus w a du dx where x I e to x I plus 1 e are the limits. So then further we can basically if we put the values of here if you put the values as I is equal to n minus 1 at the top, then we can get that x I 1 to x n a dw dx du dx plus c w u minus w q dx minus w x 1 e a du dx x 1. So accordingly the other terms for x 2, for x 3, for x 4, etc. So similarly, so this is the nth term, that is w x n e a du dx x n e, where a and c are coefficients, w is the weight function, q represents the source term, q I, capital Q I are point sources at interior nodes x I, and x a x b denotes the global coordinates of the endpoints of the element omega e. So if nodes 1 and n are the endpoints, then q1 e and qn e are unknowns, while all other q I e are known. So that is the applied point sources. So here x I is the global coordinate of the ith node of element omega e. If nodes 1 and n denote the endpoints of the element, then q1 e and qn e represents the unknown point sources, and all other q I e are always known. that is applied point sources following the Rayleigh-Ridge procedure developed for u and the shape functions, that is psi I, psi 2 to psi n for w into the weak form to obtain n set of algebraic equations, which can be written as follows. So, integration x a to x b a dw. So, dw is now replaced with the shape function, that is psi I, and for when I is equal to 1, the expression becomes d psi 1 by dx summation of j is equal to 1 to n u j d psi j dx. So, please match it with this weak formulation that we have discussed before, and the similar thing we are trying to write over here, and and plus c psi 1, that is the c u w that is written over here, c u w. So, you can see over here. So, from here we can write. So, instead of w we are putting the shape function, that is psi 1, because I is equal to 1. So, and because as we know that u is the summation of j is equal to 1 to n u j e psi j e psi j x. So, that is why we are writing here. So, again in spite of u we are putting this expression of u over here, dx minus integration x a to x b, this is w q dx. So, in place of w again we are putting the shape function value, that is psi 1 minus w x j q j e, and we are putting psi 1. So, when similarly if we are writing it for when the I is equal to 2, the expression becomes like the second line, and then when it is I is equal to I, then in place of w we are writing as psi I. So, likewise you can see over here we are replacing psi 1 and psi 2 by psi I, and then when we are writing for the nth equation, so then when I is equal to n, then the shape function so then becomes psi n. So, you can see the resultant expression of the weak formulation. So, from here we can see that the numbering of the algebraic equations follows that of the primary variables in the element. So, the ith algebraic equation can be written as over here you can see. So, here all these terms are abbreviated as k I j u I j e minus f I minus q I, where I is equal to 1 to n. So, what is k I j over here? So, k I j you can get from here. So, if you just compare it with this expression, so any of this expression, specifically this nth expression, then you can get that k I j is nothing but a d psi I dx d psi j dx plus c psi I psi j dx is equal to b psi I psi j. That means it is again a bilinear term like we told before, and f I is the integration x a to x b q psi I dx, that is the force vector or source vector. So, note that the interpolation property is used to write. So, summation of j is equal to 1 to n, the shape function psi j x I q j e is equal to q I. So, what is the partition. So, here the rule which is applied over here, that is called the partition of unity. Partition of unity, so according to that, so we know that when I is equal to j is equal to 1, or when I not equal to j, it is value becomes 0. So, that is how following that we can write that summation of j is equal to 1 to n psi j x I q j e is equal to q I, and then we can write the set of element equations for individual nodes. The equations can be expressed in terms of the coefficient k I j e f I and q I e as this. So, it is so k 1 1, that means it is all about k I j. So, that means it is if I just draw a grid like this, and then if it is say this is the I j point. So, this is I plus 1 into j, here it is I minus 1 j. Similarly, it is this is I j plus 1, here it is I j minus 1, likewise. So, for each individual nodes we are getting a element this a nodal equation of the so k 1 1 u 1 q 1 2 u 2, that means I is 1, j is also 1, here I is 1, j is 2, so and uj, the value of j is 2. So, likewise we are getting the individual equations which are called nodal equations, and then finally we can write it in the matrix notation. So, the linear algebraic equation can be written as, so here this is the K, that is the stiffness matrix, and then it is the U, which is the primary variable matrix that we are evaluating in this finite element formulation. I mean, we are developing this formulation to evaluate the value of the primary variable, that is U, and then so I mean K matrix into U matrix is equal to F plus Q. F is the source vector or force vector, and then Q is the secondary variable matrix. So, likewise we can arrive at the, this is the form of the finite element equation for in the matrix form, and solving this we can estimate the values of the primary and the secondary variables. So, after the finite element method, so now let us move into the boundary element method. So, how boundary element method is different from finite element method is that in case of BEM we do not discretize the whole domain as we do in case of finite element method. So, that is why it is computationally less expensive, and also it is suitable for problems which deals with the very large infinite domains. So there it becomes much easier to achieve a solution by employing boundary element method. So, it is basically BEM reduces a n dimensional problem into a n minus 1 dimensional boundary only problem. For example, a 3D domain problem become reduced to 2D boundary problem when we apply boundary element method technique, and when we in case of a 2D domain problem it reduces to 1D boundary problem. And then the next thing is use of Green's function. So, BEM reformulates the governing partial differential equations into boundary integral equations using Green's functions. So, these fundamental solutions satisfy the PDEs for unit impulses, enabling the transformation of domain integrals into boundary integrals. And third point is the boundary discretization. So, the boundary tau is divided into smaller elements, that is line segments in 2D, surface patches in 3D, and physical quantities such as the field variable u and its derivative del u del n with respect to the normal are approximated at these boundary elements. And the conservation laws. So, BEM inherently conserves quantities such as heat, mass and momentum by satisfying the governing partial differential equations and boundary conditions exactly within the integral framework, and its applications encompasses the problems as I told before involving infinite domains such as wave propagation, heat conduction for in a large area, and also in case of complicated geometries where finite element formulation becomes too expensive and time consuming. So, now let us start with the boundary element method formulation, reducing the PDEs into the in the form of matrix based algebraic equations. So, for that we need to introduce the idea of linear operators, which is one that we have seen using informally for most of the class. A linear differential operator denoted L is a function such that L is equal to dn to by dx to the power n plus p1 x. So, as we are increasing the order over here, and then we have to deduct it from the the power of the derivative. So, that that means p1 x dn minus 1 dx to the power n minus 1 plus, when we are writing for p n minus 1 then it will be dn plus dn minus n plus 1. So, it becomes d by dx. So, likewise, and then so this is for one dimensional problem, and in case of 2 dimension the expression can be has to be written in a with involving both x and y coordinates. So, it becomes the linear operator becomes L is equal to del n by del x to the power n. So, then when we are talking about 2 dimension, then it reduces to partial derivative plus p1 xy, which is a function of xy, del to the power n minus 1 by del x to the power n minus 1. So, the similar methodology that we are following like we have discussed just above in case of one dimension. So, so moving ahead, so let us assume a so the linear operators. So, the all linear operators in case of boundary element method have the property for such as L function of alpha u plus beta nu is equal to alpha L u function of u plus beta L function of v or nu. So, where alpha and beta are constants and u and nu are functions. So, the adjacent operator L asterisk is the function that makes integration domain integration L function of u nu d omega is equal to integration omega u L asterisk function of nu d omega. So, fortunately many operators are self adjoint. So, that L becomes equal to L asterisk even if L is not self adjoint. Usually L and L asterisk are similar functions that differ by a plus minus sign in one or more terms. So, example of a self adjoint operator. So, for example, if we consider L is equal to d2 d2 by dx2 plus 1 on the interval 0 to 1, then L function of u it becomes d2u dx2 plus u. So, now now the formulation is quite similar with that we have seen in case of Galerkin method in FEM, that is the weak formulation of a PDE. So, here similarly we are trying to integrate between the interval 0 to 1 the above PDE, that is d2u dx2 plus u, by multiplying it with a weight function w, and so then this is the resulting expression that we are getting, and then so it becomes equal to the so then now if we are doing the integration by parts, so then how it becomes? So, it becomes d dx of du dx into w, okay, into dx. So, this is what the form is. So, now so it resembles to the form. So, you can assume it as dv dx u dx. So, as we know, so then it will by integration by parts. So, we know that it will be reduces to u v minus v du dx dx. So, if you just now put the because we have considered w as u and du dx as v. So, then you can come to that resulting form. So, you can see that u v, that means this is w into u u v, w is u. So, here you can see that term, and then dv dx. So, v is du dx. So, then v becomes that du dx minus integration v. So, here v is du dx. So, here this is the v term and du dx means dw dx. So, this is how we are doing applying the integration by parts, and we are arriving at this expression. And then if we if we further reduce it, then so du dx w 1 0, and again if we apply the integration by parts rule for this integral, then we finally reduces it to the below expression which is shown here. So, which is equal to boundary terms plus integration domain integration u L function of nu d omega. So, this is how we are getting the self adjoint operator integrated. So, so since the function w was arbitrary, we can assume that w and dw dx are both 0 at x is equal to 0 and x is equal to 1. So, that the boundary terms drops out. Consequently, we get that integration 0 to 1 L function of u nu d omega is equal to integration 0 to 1 u L function of nu d omega. So, this operator is self adjoint. So, why we are confirming this? We are confirming this from this expression. So, you can understand that we are finally arriving at this expression from this expression. So, we are calling, so L u nu d omega, from here we are getting this u L function of nu d omega. So, that is why the operator is self adjoint. So, in case of boundary element method, the characteristic of the method is, in this case the weight function, that means w, by which we are multiplying the PDE and then integrating it to make it equal to 0. So, that weight function has to be the fundamental solution of the PDE. So, that means that PDE which have a fundamental solution only that can be solved using boundary element method. So, this is also a difference with finite element method that we are observing in case of boundary element method. So, here let us consider a simple equation, that is Laplace equation. We all might have studied it at some point of time. So, it is which is the del square u del x square plus del square u del y square, that means basically grad square u is equal to 0. So, along with some boundary conditions. So, the fundamental solution or for free space Green's function satisfies the equation d2w dx2 plus d2w dy2 plus delta I mean eta minus x zeta minus x comma eta minus y is equal to 0 on the domain which encompasses as x greater than minus infinity less than infinity and y greater than minus infinity less than infinity. So, here delta is the Dirac delta function in 2 dimensions representing a point source of infinite strength at eta zeta. So, in boundary element method the fundamental solution will be used as the weighting function in the integral equation as I told you earlier and is analogous to the test functions nu in finite elements. So, transforming the Laplace equation to radial coordinates where the radius r is measured from the point eta zeta, we can get transforming the Laplace equation. So, it becomes grad square w is equal to 1 by r del r r del w del r plus 1 by r square del square w by del theta square equals to 0. So, where the radius r is equivalent to, because we are measuring from from the point eta zeta. So, it becomes root over zeta minus x square plus eta minus y whole square. So, this is with this. So, here the term delta has disappeared from the equation because it is only non-zero when r is equal to 0. So, now the delta function is acting as a boundary condition that says that w tends to infinity as r tends to 0. So, the del square w del theta square term is also 0 because we have an infinite domain. So, the final equation reduces to from here this is this part it becomes equated to 0. So, which has the following solution, that is w is equal to a ln r plus b. So, this solution satisfied the boundary condition at r is equal to 0 since ln r tends to infinity as r tends to 0. So, but so far we have no information on how to find a and b. So, looking back at the original equation in Cartesian coordinates, we can integrate so that it becomes integration of grad square w d omega, that is the initial expression that we have discussed. So, now we are integrating this equation to achieve the fundamental solution. So, then the integration domain integration grad square w d omega plus integration delta into zeta minus x eta minus y d omega is equal to equating it to 0. And then, so if this zeta eta becomes tends to the omega, the domain. So, then integration omega delta zeta minus x comma eta minus y d omega is equal to 1 since omega is arbitrary. So, we will assume that eta zeta eta zeta is equivalent to the epsilon, and so so eta zeta equivalent to the domain omega. So, here there is a typo. So, there should be the domain omega. So, this means that integration domain integration grad square w d omega is equal to minus 1. So, since omega is arbitrary, we can assume that it is a circle of radius eta greater than 0 epsilon greater than 0 centered at r is equal to 0. So, with this we have to now apply the Green-Gauss theorem. So, according to the Green-Gauss theorem, we can write that integration domain integration grad square w d omega is equal to integration del omega del w del n ds, where n is the normal vector and this s is the distance along the path. So, there is a typo. So S is the distance along the path counterclockwise. So since r and the normal vector n will always point in the same direction when omega is a circle. So this is equivalent to integration del omega del w del r ds. So we are replacing n by r, the radius of the circle. So but since we know that that w is equal to a ln r, again there is a mistake. So w is equal to a ln r plus b. So we can find del w del r is equal to a by r is equal to a by epsilon, and we have that so integration 0 to 2 pi epsilon a by epsilon ds is equal to a 2 pi epsilon. So then we already know that we have discussed in the last slide that domain integration grad square w d omega is equal to -1. So hence we are putting this value over here and then we are equating it with -1. So from here we can estimate the value of the coefficient a. So then a becomes equal to -1 by 2 pi. So since we have no good way to find b, it is usually set to 0 for convenience. So the fundamental solution to the Laplace equation, that means grad square w is equal to 0, is becoming this. So w is equal to -1 by 2 pi ln r. So then now we have found the fundamental solution. Now we can use it as a weighting function to achieve the set of algebraic equation, matrix based algebraic equations by applying boundary element method to the same equation, that means the Laplace equation, that we will be discussing next. So here now we will discuss about how we can derive the boundary element based algebraic equations in 2D. So exactly like in the finite element method that we discussed earlier, we are trying to solve a PDE by using a weighted integral equation. So in this example we will look at the Laplace equation, but BM can be derived for any PDE for which we can find a fundamental solution. So so this is the most important thing, that we have to get a fundamental solution to the PDE to apply BM to solve it. So once again we begin by multiplying the PDE by a weighting function w, and and integrate it over the domain to find the weak solution. So what is the Laplace equation? That is grad square w is equal to 0. So now we are basically grad square u is equal to 0. So now we are multiplying it with the weight function, that is w. So then our resulting equation, so after we are integrating it over the domain and then equating it with the 0. So this is basically the weak form of the Laplace equation. So it is quite similar to the weak form that we have discussed in case of Galerkin method, in case of finite element method when we have discussed that. So now using the Green-Gauss theorem we can get that integration grad square u w d omega is equal to del u del n w ds minus grad u grad w d omega. So now again we have to apply the integration by parts formula over here, and then integrating by parts again in order to get a second derivative on the weighting function w. So we can achieve from here. So the next step, grad square integration grad square u w d omega is equal to we are getting from here integration del u del n w ds minus from here based on integration by parts we are arriving at the expression this. Okay. So so this shows that the Laplace operator is self adjoint. So in finite element method we choose simple piecewise polynomials as our weighting functions, but in case of BM we will choose the fundamental solutions, so that the last term becomes, so here you can see that integration u grad square w d omega, that is we have discussed shown earlier. So here we are getting is equal to minus integration u delta eta zeta minus x eta minus y d omega is equal to minus u eta zeta. So assuming that eta zeta equivalents to the domain omega and not on the boundary. So this gives us the boundary integral equation. So which is the boundary integral equation? So here now we have found this this value of this part of the equation. So now we are putting it back over here, putting this value back in this equation. So and then equating it to 0. So, then I mean we are getting as minus del u del n w ds plus del w del n u ds, and because we have already evaluated the value. So, plus u eta zeta is equal to 0. So, we are taking to the right hand side, so that is why the sign changes, and then we are basically now we will discuss how we can achieve, can develop the matrix based algebraic equations in case of BM. So, to formulate the algebraic equations in BM, we need to divide the 2D domain up into n boundary elements or subdomains tau I. So, we will make several assumptions about the elements and the functions on the elements. So, we will be given either u primary variable or q which is equal to del u del n on a given element tau I. So, boundary element method will be used to find the other. So, each element has one node at its center. So, we will assume that both u and q are constant on each element, even though the exact function q is equal to del u del n would have a lower order than u. So, this is called an isoperimetric formulation. And so, like in a finite element method, it is possible to define nodes at the end of the elements and use linear functions, or to define 3 nodes per element, that means use of quadratic elements, but we will constrict our focus to constant elements because they are the simplest ones. So, because each element has only one node for constant elements, so u and q are not continuous on the boundary. So, the boundary is always smooth for constant elements, since we are always evaluating the function at the midpoint of the line connecting the two edges of the element. That means, we are we are evaluating, so assume this is a boundary element, constant boundary element. So, we are evaluating at the midpoint here. Okay. So, as a consequence, C p is equal to minus is equal to 0.5. So, hence we have seen this equation before. So, so this equation now we are making it converting it into the boundary element a matrix based algebraic equation. So, then we are putting multiplying the ui by Cp. So, Cp is 0.5. So, half ui plus integration del omega u del w del n ds is equal to integration w del u del n ds. So, then half ui. So, then if we can write in the form of series. So, summation of j is equal to 1 to n, because we have divided the domain by with n elements. So, the integration tau j u q bar asterisk, because here we have told that we have defined q as del u del n, and here we will define q asterisk as del w del n. So, putting the value of both q and q asterisk over here. So, then we can replace del w del n and del u del n as q asterisk and q. So, then writing accordingly from this equation we are arriving at this expression. So, here since u j and q j are constant on each element. So, you can quite effectively write that from this expression we can arrive at this expression as half u I plus summation of j is equal to 1 to n u j, because u j and q j are constant. So, they are coming out of the integration summation of tau j q asterisk d tau is equal to summation of j is equal to 1 to n. Again, for because of the similar reason, as u came out of the integration, q also came out because it is the constant. So, integration tau j w d tau. So, this gives two integrals that we need to approximate, which we are terming as h I j and g I j. So, we are terming q asterisk d tau integration tau j as h I j, and we are terming integration tau j w d tau as g I j. So, these integrals give the influence of some node j on the fundamental solution, that is centered at I on the boundary, and are called influence coefficients. So, now for a single point I on the boundary, we can write as half u I summation of j is equal to 1 to n u j h I j is equal to summation of j is equal to 1 to n q j g I j. So, u I is equal to u I values of u 1 u 2 dot 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 u n, and similarly for q 1 q 2 dot dot q n. So, since half of all the q I and u I are specified by boundary conditions, we need n number of equations. So, this is accomplished by moving the singular point I around the boundary and evaluating at every node I is equal to 1 to n. So, for simplicity we can define Hij is equal to H bar Ij when I not equal to j and is equal to H bar Ij plus 0.5 when I is equal to j. So, so which becomes the matrix equation, that is now Hu is equal to Gq. So, where H and G are n cross n matrices and U and Q are vectors of length n. So, from here we are arriving at here. So, except the boundary nodes, in the boundary nodes this equation reduces to this. Okay. But we will see how we can formulate the matrix equations for the domain interior in the next slide. So, then if we expand these matrices we can arrive at this like H11, H12 dot 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 H1n. So, you can see over here like we have written Hij. So, Hij so one is row, another is column. So, so this is for first row H11 first column, H12 second column, H1n nth column. Similarly, second row first column, second row second column, second row nth column, and then U is a column vector with n number of rows, and similarly for G is a n cross n matrix and Q is a column vector having n number of rows. So, to solve the linear equation, all unknowns are placed on the left hand side of the equation and all knowns need to be moved to the right hand side of the equation. So, this reorganization involves shuffling the matrix columns. Example, suppose the boundary is divided into 12 elements. So, U is known for the first 6 elements, that means I is equal to 1 to 6, and then Q is known for the last 6 elements, that means I is equal to 7 to 12. So, what we need to do, because as we discussed above that all unknowns need to be moved to the left hand side and all knowns to the right hand side. So, we reorganize the matrices and then we are arriving at this matrix from here, and where we have already placed all the unknowns at the all the unknowns at one side and all the knowns at another side, that we will see in the next rearrange matrix. So, here you can see the rearrange matrix. So, where Q1 to Q6 is unknown, U7 to U12 is unknown, and here in the right hand side U1 to U6 is known, Q7 to Q12 is known. So, now we are very much capable to identify the solutions, because we so the unknowns are shifted to the left hand side and knowns are shifted to the right hand side. So, this process results in a property structured linear system ready for computation. So, the rearrange matrix equation for solving U and Q values on the boundary using the boundary element method. So, it is structured as below, as the rearrange matrix that we have discussed. So, the so this system is can be represented as Ax is equal to F, where the value of x can be found by doing the matrix inversion, that means x is equal to A inverse F. So, advantages: solving a 1D problem on the boundary instead of a 2D problem in the domain, that is the advantage of using boundary element formulation. So, this results in a smaller denser matrix compared to methods like FEM. Although computationally more expensive due to the dense matrix A, it is efficient for boundary only calculations. That means, BEM is only effective for very large domains, but in case of smaller domains FEM is a better technique to go forward to. And so, the solution using, as I told you, x is equal to A inverse F that we are getting from here, we can compute the unknowns Q and U for every point over the boundary. And in order to find the value of U at some point in the interior of the domain, that means assume this is your domain. So, if you have to find a value at interior point, so then we go back to the equation that we have written earlier. That means, so this is the this is the form that we have written earlier. So, we are going back to this form, and then we are writing it as so ui is equal to wq d tau minus uq asterisk d tau. That means, it is nothing but, because we already know, we have approximated this as qj gij and this one as uj h bar. So, then frequently we are not only interested in the value of u at point I, but also the flux in the x or y direction. What is flux? That is q. So, we can find the flux in the x direction from this expression. So, where q I x is equal to del u del x and which is equal to integration tau del w del x I q d tau and so minus integration tau u del q asterisk del x d tau. So, where there are no partial derivatives of u and q because they are constants along each element. So, so putting in the element mesh we can find q I is equal to summation of j is equal to 1 to n q j integration omega tau j del w del x d tau minus summation of j is equal to 1 to n u j integration tau j del q asterisk del x d tau. So, notice that because we are looking at the x direction flux, the term del q asterisk del x is a mixed partial derivatives. So, typically all the integrals in BM are integrated numerically using quadrature rules just like in finite element method, since in BM the integrals have complex functions inside. So, it is typically necessary to use higher order approximations. So, with this we are finishing the introductory module of this course, and then we will go ahead in the next class with the first module of the course, that is casting and process modeling. So, till then, bye.